Welcome to the first learning outcome, where we look at static equilibrium. That is, what keeps a mechanical system perfectly still. We'll meet forces and moments, and the three simple conditions that guarantee a body stays at rest. Let me give you a quick map of where we're heading. We'll learn how to spot when a system is in equilibrium, how to break awkward angled forces into horizontal and vertical parts, and how to handle both forces meeting at a point and turning effects. Along the way, we'll pick up some neat graphical tricks, the triangle and polygon of forces, and Bose notation, and we'll lean on three conditions throughout. The sum of the horizontal forces is 0, the sum of the vertical forces is 0, and the sum of the moments is 0. So what do we actually mean by static equilibrium? A body is in equilibrium when it isn't accelerating, and if it's static, it's also completely at rest. For that to happen, two things must be true. The net force on it has to be 0, and the net turning effect has to be 0 as well. It all comes straight from Newton's first law. If the acceleration is 0, then the resultant force must be 0 too. It's exactly this principle that lets engineers design bridges, cranes, and buildings that stay put under load. Let's get a few key words straight before we go further. A force is simply a push or a pull, measured in newtons, and it's a vector, which means it has both a size and a direction. When several forces act together, the single force that would have the same effect is called the resultant. The equilibrant is its mirror image, the one force that balances everything and holds the body still. And a reaction is the supporting push that a surface or a support gives back to the body resting on it. Here's why we treat force so carefully. Because a force has both magnitude and direction, we can draw it as an arrow. The length shows how big it is, and the way it points shows its direction. Two equal forces pointing in opposite directions simply cancel out. So when we combine forces, we can't just add the numbers. We have to respect their directions. And that's precisely why we resolve them into components first. One force that's always predictable, though, is weight, which acts straight down and equals mass times g. Now to the heart of the whole outcome, the three conditions for equilibrium. For any flat or coplanar system, all three must hold at once. First, the horizontal forces must balance, so the sum of the forces in x is 0. Second, the vertical forces must balance, so the sum of the forces in y is 0. And third, the turning effects must balance, so the sum of the moments about any point is 0. If all three are satisfied, the body simply won't move or rotate, and these equations are what let us pin down unknown forces and reactions. Let's see how we split a force up. Take any force F acting at an angle θ to the horizontal. Its horizontal component is F times the cosine of θ, and its vertical component is F times the sine of θ. Put those two together, and they have exactly the same effect as the original force. The beauty of this is that it turns messy angled forces into tidy sums in x and y. And there's a handy check. The square root of fx squared plus fy squared should give you back the original size of f. Let's work one through. A tow cable pulls with a force of 100 newtons at 30 degrees above the horizontal, and we want its two components. The horizontal part is 100 times the cosine of 30 degrees. The cosine of 30 degrees is 0.866, so that's about 86.6 newtons. The vertical part is 100 times the sine of 30 degrees, and since the sine of 30 degrees is 0.5, that comes to 50 newtons. As a check, the square root of 86.6 squared plus 50 squared brings us right back to 100 newtons. So the cable pulls with 86.6 newtons horizontally and 50 newtons vertically. Let me introduce a special and rather convenient case. Coplanar forces all lie in the same flat plane, and concurrent forces all pass through one common point. Because they share that point, none of them can produce a moment about it, so the moment condition looks after itself. That means we only need two equations. The sum of the forces in X is 0, and the sum in Y is 0. Think of three ropes meeting at a single knot. We resolve each force, set the totals in X and Y to 0, and we're done. Here's a nice example. A ring is pulled east by 60 newtons and north by 80 newtons, and we want the resultant, plus the equilibrant that would hold it still. Since the two pulls are at right angles, Pythagoras does the job. The resultant is the square root of 60 squared plus 80 squared, which is the square root of 9,000, or exactly 100 newtons. Its direction is found from the tangent of the angle, 80 over 60, giving about 53.1 degrees north of east. The equilibrant is just the same size acting the opposite way, 100 newtons pointing 53.1 degrees south of west. There are really two routes through any equilibrium problem, and it's worth knowing both. The analytical route means resolving forces into components, applying the sums in X and Y equal to 0, and solving the algebra. It's precise and gives exact answers, but it does need your trigonometry. The graphical route means drawing the forces to scale, tip to tail. If the figure closes up, the system's in equilibrium, and you can measure the unknowns straight off the page. It's quick and very visual, though only as accurate as your drawing. Let's look at the first graphical tool, the triangle of forces. It applies when exactly three forces act at a point in equilibrium. You draw them to scale, head to tail, one after another. If the body really is in balance, the triangle closes perfectly. The finish lands right back on the start, and that closure is simply another way of saying the resultant is 0. Any unknown sizes or directions can then be scaled straight off your drawing. In effect, it's a picture of the sums in X and Y both being 0. Let's try it with a hanging load. A 400 Newton weight hangs from two cables, each at 30 degrees to the vertical, and by symmetry both tensions are equal, so we'll call each one T. The three forces are the weight pulling down and the two tensions. Balancing vertically, the upward parts of the two tensions must carry the weight, so 2T times the cosine of 30 degrees equals 400. The cosine of 30 degrees is 0.66, which gives 1.1732T equals 400, so T is 400 divided by 12, about 231 newtons. Each cable therefore carries a tension of roughly 231 newtons. When more than three forces meet at a point, we simply extend the idea into a polygon of forces. You draw each force to scale, head to tail, taking them in turn. If the polygon closes, the forces are in equilibrium. If there's a gap left between where you started and where you finished, that gap is the resultant, and reversing it gives you the equilibrant. It's especially handy at a joint where several members come together. Bow's notation is a tidy labeling system that keeps force diagrams from becoming a muddle. The trick is to letter the spaces between the forces with capital letters. So each force is then named by the two spaces it sits between. A force might be called AB, for instance. On the force diagram itself, that same force appears as the line little a little b. It sounds fussy, but on a big framework it keeps everything clear and helps you avoid mistakes, which is why it's so widely used for pin-jointed frames. Let's put it to work on a wall bracket. A 500 Newton load hangs at the joint, where a horizontal tie and a strut at 30 degrees to the horizontal meet. We want the strut force, call it C, and the tie force T. Three forces meet at that joint, the load pulling down, the strut, and the tie. Resolving vertically, only the strut has a vertical part, so C times the sine of 30 degrees equals 500. Since the sine of 30 degrees is 0.5, that's 0.5C equals 500, giving C equals 1,000 newtons in compression. Then resolving horizontally, the tie force is C times the cosine of 30 degrees, which is 1,000 times 0.866, about 866 newtons in tension. So far we've balanced forces. Now let's think about turning. A moment is the turning effect of a force about a point, and it equals the force times the perpendicular distance from that point. We measure it in Newton meters. That's why a longer spanner gives you more turn for the same effort. You've increased the distance. Moments can act clockwise or anti-clockwise, and we give those opposite signs. For equilibrium, the sum of the moments must be 0, so the clockwise and anti-clockwise turns cancel out. Here's a quick one. A mechanic pushes with 40 newtons at the end of a spanner, a quarter of a meter from the bolt, and at right angles to the handle. The moment is just the force times the distance, so 40 times 0.25, which comes to 10 newton meters. So the turning effect on the bolt is 10 newton meters. Nice and simple when the force is already perpendicular to the handle. Let's turn to beams and their supports. When a beam rests on a support, the support pushes back up on it, and we call that push the reaction. Those reactions have to balance all the applied loads, plus the beam's own weight. To find them, we usually combine two conditions. The sum of the moments is 0, and the vertical forces balance. The clever move is to take moments about one of the supports, which makes that support's unknown disappear, leaving just one reaction to solve for. Then vertical balance hands you the other one. Let's do it properly. A light beam 6 meters long rests on support A at the left and support B at the right, with a 300 newton load sitting 2 meters from A. Taking moments about A removes the reaction there, so the reaction at B times 6 equals 300 times 2, which is 600 newton meters. That gives the reaction at B as 100 newtons. Now vertical balance, the two reactions must add up to the 300 newton load, so the reaction at A is 300 minus 100, or 200 newtons. So A carries 200 newtons and B carries 100 newtons, and reassuringly they add back up to 300. It's worth pausing to compare two ideas that are easy to mix up, the resultant and the equilibrant. The resultant is the single force that could replace the whole system and have the same effect. You find it by adding the components, Rx and y, and taking the square root of Rx squared plus y squared. If that resultant is 0, the system's already balanced. The equilibrant, on the other hand, is the single force you'd add to restore equilibrium. It's equal in size to the resultant, but points in exactly the opposite direction, and it's the force that closes your triangle or polygon. Let's see where all this shows up in the real world. On a balanced lever, the clockwise moments equal the anti-clockwise ones, so a seesaw balances when one force times its distance matches the other force times its distance. Cranes carry counterweights to keep the moments summing to 0 as they lift. Wheel nuts are tightened to a set torque, so they clamp safely. And roof trusses share their loads so that every joint stays in equilibrium. It's the same three conditions doing the work in every single case. Let's pause and test yourself. First, can you state the three conditions a coplanar system has to satisfy to be in equilibrium? Second, if a 200 Newton force acts at 60 degrees to the horizontal, can you write down expressions for its two components? And third, could you explain, in your own words, the difference between the resultant and the equilibrant? Have a think before we carry on. A few more terms to lock in, this time around moments and supports. A moment, remember, is the turning effect of a force. The force times the perpendicular distance. Torque is just another name for the same thing, measured in Newton meters. A pivot is the fixed point a body turns about. Concurrent forces are ones whose lines of action all meet at a single point. And coplanar forces are simply those that all lie in the same flat plane. Another quick check. First, a beam 4 meters long has a support at each end and a 600 Newton load right in the middle. Can you find both reactions? Second, why do concurrent forces need only 2 equilibrium equations rather than 3? And third, can you describe how Bose notation is used to label a force diagram? Take a moment with each before moving on. Let's finish with a reliable recipe for any static problem. Start by drawing a free body diagram showing every force and the direction it acts in. Decide on your method, resolving, or a triangle or polygon of forces. Resolve the forces and apply the sums in x and y equal to 0. Then take moments and apply the sum of the moments equals 0 to find the reactions. State clearly which principle you're using at each stage, and finally check that your answer looks sensible and the units are right.